a little planning. So therefore, yesterday we were saying, you see that we want to go to the fast algorithm. And so I did a little new planning. So therefore, let's switch to the second part. And then we can talk about maybe the fast algorithm sometimes later with this one. So this contains a lot of new stuff. Also, it's relatively easy to understand. So especially, I think this will be very useful. So the first part yesterday we were talking about mostly something very elementary about how do you use a partial differential equation for image processing, especially remove noise. So this part mostly, so it's we talk about segmentation problems. So segmentation is essentially give you an image, how do you find the object? But mathematically, it's the same thing if you want to do segmentation. You see that, so we are going to talk about, so most of the things here, we will just use the segmentation as the application. But the same idea you can use for surface construction, right? If you have a lot of points, 3D points, you want to construct a surface. So you have and then you see which point is connected to which one. That's also segmentation. Essentially, you see that you segment into two phases. So this is the phase 1, this is the phase 2, and the interface is the surface you want to. You see, data mining is the same thing. Machine learning. You see, machine learning is you want to learn the object into 10 classes. So you see, it's essentially the same. But everything we talk here, so we will use the segmentation as an application. Essentially, you see that we first go through the elementary models, and then we will talk about level set methods. Most probably we'll skip those two and go to convex relaxation, graph cut, and then there's a continuous max flow. And here's multi-phase. You see that we talk about multi-phase transverse. Multi-phase layered graph, and even continuous max flow. So those things are very, very new. It's just in the past 1 or 2 years. You solve the same thing as the traditional methods, but they are much faster and very, very stable. So I'm thinking, you see that maybe we just switch to this one, and then for the fast numerical algorithm, most probably if we get time, we can talk in connection with those things here. So therefore, you see that, so this part is mostly related to graph, cars, and PDE minimization, and especially we try to find the connection between those things. And those has been mostly done with my students, especially Aggie Bayer. He was my PhD. Even he's not in UCLA with Stan Osher. He's a postdoc. And Jing Yuan, he's a postdoc with me. A number of other students I don't mention, right? But before you see that, we go into more the detail. I give you more. You see that this will be more like an elementary. I give you a more elementary introduction. Yeah, so here I give you more elementary. So essentially, you see that, so this is just giving a warm up. So the first question that this is a photo, I'm asking what he's doing. Can you guess what he's doing? Wow, we missed the connection. Hope it comes up soon. So essentially ask what he's doing. Can you see clearly? Yeah. So this is, so we were together about, this is a colleague with me. We were together, you see, go to the mountain, do skiing there. And this is after skiing relax. He collect a lot of magazines. He want to cut something from the magazine, so that's essentially segmentation, right? This is what he did. You see that? He want to cut this, you see, very strong man and very handsome. He want to cut this one and hang it on somewhere. So therefore, this is essentially you see segmentation, right? This is the traditional segmentation. You want to get something, you cut it out. So you pick it out. This is segmentation. So therefore, you see what's the best segmentation methods? So therefore, we will say the hand assessors, right? So this is the best way that you cut what you want. You don't make a mistake, right? But however, you see this is old days, right? So therefore, now we need to do like a digital segmentation. So you see that the most simple way to do segmentation is essentially like a threshold. So you have a digital methods. So here you have a digital image. You have a two intensity. One is like a 65. So I think here this is a 65. This is about 100, maybe 180 or something. So this is darker than that one. So there's no noise in this image. So here is the histogram. So there are so many pixels taking this value, so many pixels taking this value. So if you want to segment, the simple with threshold, right? So every pixel which is maybe below this value is one region, above another value one region, and you easily get those two regions. So therefore, however, for real situation, you can never get, you see, for real application, the intensity will be more complex. So this one, you see that, so the intensity value in this region varies. Some takes about maybe 60, some take about 70. So here, some takes about 200. Even this one, you see, you have a variation of the intensity value. For this case, you can still do threshold. You see, everything below here, I say one region, every point which has the intensity above here, I have another region, and you also easily get those two regions. So this is the most simple threshold. But however, if the noise is getting bigger, you see like this one. So this is, you see a lot of points here, you have a lot of white points have a similar intensity there. Here you have a lot of black points inside this region, you have intensity here. So for this image, if you do threshold, it doesn't work anymore, right? But if you use human eyes, if you look at this image, I still know, you see this is my region, outside is another region. So therefore, you see, if your intensity really, you see, varies, mix up, and then threshold is not working anymore. But still, I want to see, you see, that for industry application, maybe still the majority of the problem can be solved by a threshold. So I'm working as a senior scientific advisor to a company which is mostly doing a lot of, you see, the industry application. And they have a lot of segmentation problem. And most of the segmentation there is a simple threshold is enough. You never need level set or so complicated things. But however, if the application is complicated, if the threshold doesn't work, and then you must find more you see, advanced. You see, like that one. A lot of application could be much more complicated like that one. So therefore, you see that this is this is the application. You see that here, this is blood cells. And if you do segmentation, threshold mostly works. But you see that this is one of the standard textbook examples. So here is rice. But you see the background here is white. The background here is black. If you do threshold, you see that. So in this region, you get something wrong. You get something wrong. Right. So this is the simplicity segmentation, even it doesn't work. Also, you see, like typical, I think, you see, for segmentation threshold segmentation, I think K-mean or something which is related to K-mean seems to be the most commonly used segmentation method for real application. You see that this is a real example for K-mean. So therefore, this is the input for something from the galaxy. If you use a K-mean to segment each point, you get a class. I think you get 4 classes. This is one class, the white point one class, blue point another class, black point. There is 3 classes or 4 classes. So in this, for this image, so every pixel, if I use a K-mean, I know which class I belong to. So each pixel, each point, you get a class. But however, you see that for segmentation, I really want to see this is my region, but it doesn't get you the region. So this is, you see that this is the typically a problem with the threshold. So it doesn't tell you the region. What you want, you see, I want to identify the object. So for those situations, but so for most real applications, threshold plus a little bit. You see here, if you do morphological operation, you take the small points. If the piece is smaller than a given size, you merge it with the neighbor. So this kind of morphological operation for real industry application, you can do that one. So that mostly make the problem to work. That's enough for software or for one company. But if you want to make a more general method, this kind of thing doesn't work. You see that? If you do morphological, you see elimination, a lot of the small points can be eliminated, which means a region which is smaller than given size, except that this is not a region, you merge it with a neighbor. So that you can do. But that's some kind of, you see, like a regularization. And so you see that most of the methods when you talk, you see, will try to overcome those kind of things. Yeah. So therefore, you see that threshold is so simple. You see, just look at the point. I see, you see which class you belong to. That's so simple. So therefore, if you want to get rid of those problems, mostly you need to use variational methods. So variational method, if you check the dictionary, is what's variational? Which means a variation means a change in the value of the function due to small changes in the value of its argument or arguments. So that means you see that you do something, you perturb it. If the function value is changing, mostly if it's getting smaller, so that's something you want. So therefore you see most variational methods is related to some kind of minimization, because you vary something. If the value reduces, I think it's good. If it reduces more, it's good. If it doesn't reduce, and then you can't go any further. So therefore, most of the variational methods are minimization approach. So threshold, it's not variational, right? So you don't minimize, you don't vary something, right? So therefore, you see, variational methods are often used to treat those complicated problems. I think the first variational method is the so-called Sneek Model. The first, and this is still commonly used in medical applications. So the Sneek Model is essentially regard the curve. You regard the curve as a snake. So I draw a snake. So therefore, you see that you want to move this curve. And so ideally, when this curve moves at the boundary you want, and then you should stop. So you should stop to move it anymore. How do you do that one? So essentially, you assign the curve or snake energy. So you have two kind of energy. One called the internal energy, another called the external energy. So therefore, you see that this is a Sneek model. In fact, later we see that this external, internal is very easy. It's related to elasticas. So when the method was originally proposed, they assign energy to the snake, internal, external. So therefore, the internal energy of the snake is essentially the length plus the bending energy. It's essentially the elasticas. So therefore, if the snake is long, have a lot of bending, you want to minimize the energy, so you will shrink the length, you will make the snake, you see, less bending. And that's internal. So external energy essentially is like, if you want to segment this image, so the boundary is very blurred. So the external energy is essentially, you see that you take the gradient of this function. You take the gradient of this function. And then you see 1 over 1c. C is mostly a given constant. And so this is a plot of this function. And so this function is mostly called the edge detector. So you can see that this function has the smallest value on this curve. In the other places, it's higher value. So therefore, the external energy is essentially the integration of this function over this snake. The internal energy is the length, is the elasticas of this one. So you minimize a mixture of those two energies. And this is essentially the Sneek model, right? And for this image, so therefore you see that if you start with a curve which is around this egg, and then the external energy will shrink the length. So the curve will shrunk. But you see, once it shrunk, and suddenly you see the curve is getting here, and then suddenly will fall into this edge valley. And then you see that it cannot shrink anymore. So that's essentially the Sneek model. That's one of the variational model. So therefore, you see that variational model is very easy to implement. We can even talk more a little bit later how to implement it. But you see, mostly only works with the simple curves. So you start with a big curve, shrunk, and stop here. It's a little more common. You see, like this one, if you want external mostly works. Also computationally fast, but mostly it doesn't work for very, very complicated curves. You see, like such a curve, you see that you have a lot of oscillation, you have a host. If you want to capture all those curves, the Sneek model doesn't work. Smooth. So therefore, this is the reason you see why the level set is coming in. So therefore, level set, they can track very complete curves, and then you see Stan always see, you see one good point of a level set is emotionless surgery. Emotionless surgery, you see that if you use a Sneek model, you see if the two curves, then you see you have two curves and then you're coming, and then they merge. When they merging, you must do operation here. You see how the two curves merge together. Also, you see if one curve is suddenly coming together, if you want to split, at the point it splits, at this point, you see there mostly it doesn't work. You must do a special operation here to split the curves. And that's one of the essential things with the Sneek models. So you must do a surgery. When you merge the curve, split the curves. But level set, so we should see that there is no painless. You see when the curves merge or when the curves split. Maybe even I can show the movie. This is a movie from Jim Session, so I can show you the movie so you can see clearly. I think a lot of level set expert, you see this is already well known, but maybe still. Where's the movie? Yeah, so therefore this is the movie, the typical movie from Jim Session about level set. So therefore you see that, the level set is that when you want to move the curve, you see the Sneek model, you see you need to find the curve and then move the curve. So the level set that you don't move the curve, instead you move a function. The function up and down, so therefore you cut the zero level and then that will produce a curve. So therefore you see that like this one, so like this one you see that, you see that when you start there are two curves in the beginning, but when you move the function down, you see that these two curves slowly merge and then produce one curve. At the point where the two curves merge, if you use a Sneek model, you must do a surgery there. You must do operation. But use a level set, you see, you move the function up and down, you can produce any curve you want. So this is essentially the essential advantage of the level set methods. This is so dark, right? So therefore, that's you see, Stan always say this is a level set. We have emotionless or painless surgery. So that's the level set mostly comes after the Sneek model produce a lot of advantages, and so therefore you see level set has been used really in the past 2 decades. It used a lot of application, image processing, computer vision, fluid dynamics, inverse problem. Many other applications involves curves and surfaces, the so-called interface problem. There are many problems which are called interface problem. Where essentially you want to move something between something, those are so level set has been used in a lot of applications in those areas. But you see that still you see that you want to get something better. Even level set is very good, you still want to get better. So therefore, the one thing that you see level set, especially for image segmentation, level set depends on initialization. Later I'm going to show you one example. You see that if you use a level set method for segmentation, if you start with one initialization, you get one segmentation. If you start with another initialization, you may get another segmentation. So this is one of the problems. Still very slow for real-time application of larger size data. You see, if the data is getting 3D very, very large, and level set is still slow, so therefore you want to get it better for this one. So therefore you see that recent approaches to solve the interface problem, you see, mostly it seems that this labeling approach is getting very, very popular. So what's a labeling approach? Is a level set is that you see that if I want to find the region boundary, I move the curve of the boundary. You move it around, move, and then you see in the end, it gets to somewhere you cannot move anymore. Even you move, the energy doesn't reduce, right? So that's you move the curve. So the labeling approach that you see like for this one, I want to partition the region into 3 parts. The black part is 1, the gray part is 2, white part 3. I want to partition these 3 parts, but you don't know which partition is correct. So therefore you see there are many possibilities of a partition the region. There is one partition which produces the smallest energy. You see that how do you do it? Essentially I give a label. So therefore this region, you see I give a label, another region give a label. If the label you see, and then you minimize with the label. So therefore you see that this is one way to label. So therefore I give a label 1 here, label 2, label 3. So this is a label function. And so therefore this label function take 1 value here, 2 values, 3 here. You just minimize with respect to the labels. And normally I tell you how many labels I want. You see, if I need 3 regions, I only have 3 labels. If I have a 4 region, mostly I tell you how many regions I want. Right. Instead of moving, you see the level set move the curves, and this labeling function, you see, just modify the label. You see that this label does not minimize the energy. You can move to here, maybe you can move to there, the energy reduce, and then you move in the end, you can't move anymore. So therefore you found one label which minimizes the total energy. So this is so-called the labeling technique. You see that if the label is given, and then the corresponding characteristic function. So this is a characteristic function for region 1. This is a characteristic for region 2. This is a characteristic for region 3. So what's a characteristic function? The characteristic function for a given region that is equal to 1 in that region, equal to 0 everywhere else. So if the label is known, the characteristic function are known. So therefore you see that one approach you minimize with the labels. There's another approach you can just minimize with the characteristic functions. So once you get the characteristic functions, and then you get the regions. So those are the new approaches which has been very active during the last, you see, half year or 2 years. So I'm going to talk, you see, a lot of things related to this one. So you solve the same problem. Instead of using level set, you can use all those things. Yeah, so therefore you see that you can use a level set or to segment this image, but use a labeling function. You see that you get, so this is region 1, this is region 2, region 3, region 4, region 5. So therefore you get the labels. Mostly you see that this region is the background here. And this star is this one, and this is, so this star has the same intensity as the background. And this star has the same intensity as this background. This star has the same intensity as this is the star over here. So therefore this is use the labels instead of using level set to really do the segmentation. Yeah. So the problem is how to solve the labeling problem. You see level set, we are going to talk about how do you solve the level set, and then you just use a gradient descent. But how do you solve the labeling problem? So therefore essentially there are several approaches. So one approach is to use a graph cut approach. So we are going to talk maybe even, you see, maybe I can jump to talk about those things. You can use a graph cut. But have you heard about what's a graph cut? Have you ever heard about what's a graph? We are going to talk about what's a graph cut. And this was essentially, you see, a graph cut for segmentation I think was known much earlier, but in fact it was a Boykov or Kolmogorov in 2001. They make this very popular. In fact, if you look more carefully, that's essentially one way to solve the labeling problem. And then there is another approach is to use a global convex relaxation. So this we are going to talk, and then there's a number of people working on this one, include our group has been working on this one. Also you see in the end we should talk about continuous max flow. So this is, you see that make a continuous version out from the graph cut. And this is especially something very, very new, very, very new. So graph cut is essentially, I'm going to talk about those ones a little bit later. So this is a 1D graph, this is a 2D graph I should talk about later. And convex relaxation, you see that essentially you see that for many of the problems, in the end, it becomes a minimization of a function. Mostly, this A is the number of pixels, so it could be several million, very, very huge. So therefore, you see that level set is not convex. It depends on the initial value. So therefore, essentially, what you do that. So you see that this is mostly the level set minimization. If you start from here, you get stuck here. If you start here, you get stuck here. If you start here, so therefore, it depends on where you start. Where you start. You are trapped into local minimizers. So therefore, the convex relaxation that you see that I try to modify the energy function of the level set or something which is not convex. You try to get a convex envelope. You try to get a convex envelope. So therefore, the convex, so this convex function will be very easy to minimize. And so therefore, in most of the, you see, in the very good cases, the convex function have a unique global minimizer. And this unique global minimizer coincide with your original one. You see that the global minimizer is a coincide, they are the same. This turns out for the special models, this is a case. We have a proven. We have a proof even for, you see, for the approaches involved with TV. TV has a very special geometrical. But very often you see this may not be correct. So therefore you see you have a non-convex function. Right, you have a non-convex. If you do global, so therefore maybe your global minimizer here, and then you see that they are not exactly the same, but they are not far from each other. They are not far from each other. Can you see? And then can you use some mathematical methods? You see from here you get something which is very close to that one. So in case if it doesn't give you exactly the global minimizer, but in fact this does happen for TV. With a total variation, we have a proof for that one. It does happen. I will also give details on that one. Also, you see how to convexify a function. You see there are standard ways. You see any function you can find a convex envelope. That's very, very easy. But for a specific problem, how do you convexify it such that this is very close to that one? So that's a little bit more tricky, and that need a lot of thinking. You need to use special properties. So the continuous max flow is something which is very recent. Essentially, you see that I will talk about graph cut. You see, graph cut. You have a graph. You maximize the flow over this graph, and mostly you get a cut, and then they say this is a region 1, this is region 2 mostly works. You see that, and then you must solve a discretized graph cut problem. So therefore, recently you see that we don't want a graph. We want to have a continuous region. We have a max flow problem over the continuous region. You see that, and then you get rid of the graphs, and then you see you have a continuous thing, and that's something very, very new. So therefore, I'm going to talk about that one. So this is a very fast, very stable, right? Yeah, here is just some testing. You see that, I guess this is not new for people working with image processing. So you can extract the object. So here is some test by one of my students. So we use a graph cut. Here we use a graph cut. We do real texture segmentation. So therefore, those are the real images, and this is a test. So therefore, use a graph cut. So therefore, here will be you construct graph. So here everything is connected to the source. Here everything is connected to the thing. You exactly get this region. And especially here is for texture segmentation. Texture segmentation, I think we have. So this is a test from this paper. Here is doing more texture segmentation. For texture, so here is a different texture. So this is, so you can see that, so here is texture 1, texture 2, texture 3, so we want to capture the texture. So the orientation is the same, but scale are different. Here is the orientation are different, scale are also different. Try to see if you can capture the textures. Here you see also you try to capture the textures, use a graph cut. So I use a new graph cut I'm going to talk about later. Here's a real test. Right. Here is also one real test. So this is a real CT scan. So this is a real machine, real CT scan. So this is the CT of object, and you see it's a scan from. This is a movie slice by slice. And this is you see we did by the graph card 3, but graph card you see that. I will talk about later. You see that this is an image very big. It's about 530 something times 530 sometimes 300. So only loading this image into the computer takes about 2G of the memory. So therefore, and then segment it and computing, and you see if you level set, and then that will take a lot of time. So graph card much faster. So therefore, if you look at this movie, can you guess what kind of object it is? So this is a real. There is no artificial noise. There is a real noise, a real scan, and this is intensity slice by slice. And this is just repeating again. I think, yeah. This is a starting. And this is the ending. So it's starting up again. And can you guess? You see what kind of a 3D object this is?
Alligator.
Huh? looks like, yeah. Any other guess? You see what kind of a 3D object this is? This is like you see in the airport if you do a scan of your luggage. You see mostly you see slice by slice, right? So, but this is not medical CT. This is an industrial CT. It's a real CT scan. And can you guess? You see what kind of object it is? Use your imagination. So therefore, and so this is a really good example to show that you see segmentation is crucial. When we get this data, the guys, they don't tell me what kind of object it is because they want us to segment it. We look at it, you see, many times. We cannot imagine. But once you segment, then you see we send them the segmented result, and it looks very clear. Right. Any other guess? Alligator is one of the guess. Any other guess? It's an industrial CT. It's not medical CT. Professor Lee?
I have no idea.
If you don't guess, the other people dare not to guess.
I just put my clothes in my bag. So.
Any other guess? Yeah, so this shows the importance of doing segmentation, especially 3D, even maybe like a 4D segmentation. Otherwise, if you only look at this image, you really, it's difficult to imagine. Even you can see it's a layer up, but it's difficult to really, you see, to imagine what kind of object it is. So this is the object. Maybe, yeah, this is, you can see more, so therefore, so you first start from below and then goes up, right? So I will show the whole 3D. So this is the object after the segmentation. I will show you, here's another one here, wow, yeah. So maybe I will show you, you see the movie. This is done by one of my master students using graph card. Is it coming? Oh, this is another one. So this is we tested about three, four examples. This is also the real CT data. You see, there is natural noise. You see, there's a lot of noise around, and there's a lot of natural noise. So we didn't add any other noise. This data is also about 2G if you load it into the memory. And so here is the segmentation result. So this is you see, you have a lot of wears. The keyboard are warming up wears, and then this is Yeah, so therefore I think this is more complicated. It's a real one. You can. It's very dark. So here is a slice by slice real CT and a very huge image. And here is a segmentation. So this is you see it's a small device of the machine. You CT scan it. So we segment it. It's very huge data. Like just load one of the 3D images take about 2G memory. So therefore, not to say compute. So here is an image you have just seen. Yeah, so here is just the movie you have seen. So this is from the bottom of the object and goes slowly up, and then you add it. You see the surface looks very complicated. So this is a segmentation of the whole object. So and then you see from the bottom. No, you see the object, right? when you see the first movie, you can hardly imagine this is the object you are seeing. This is so small. I think the real object just so small. It's something like a shell from the ocean. It's a shell from the ocean. This is the segmentation result. Yeah. So I think this is. So this is another one. This is also real image, and there's natural. You see that. Can you guess what kind of object in this one? Yeah, especially you see like there is a small circle here. Getting smaller, and suddenly is moving, and moving here, disappear. So this is So this is a segmentation. So this is So this is a small metal ring. You support it, and then you scan it from the bottom up, and the small circle is essentially the tip of the right. Yeah, so those are the real examples using the segmentation method to really segment those things. So for example, for the shell from the ocean, that one we just use 2 phases. For this one, we need to use up to about 6 phases. So essentially, we first try 2. It seems it doesn't. You miss some of the things. We increase until increase 6. You could automatically. You can start with a bigger number of phases and reduce it. Segmenting for this one really takes about. If you use other methods, it takes about many days. If you segment 2G data, right? But if you use a graph card, we can get it in a number of minutes. We can solve it. So, but still, you see, like a medical application, you just you scan the brain. Especially if you scan, you see, mostly you're laying down there for half an hour. They will scan about 30 times. So therefore, that's not the 3G, that's many G. And then even that processing of that data, you see, the doctor wants you to do it in several minutes. So that means we still need something which is even faster than this one. So therefore, you need to get something faster and faster. You see that, and never fast enough. But still, you see that. So that's the reason you see we have a job, right? We need to do something with this method to get even faster. So yeah. So those are the by level by graph card. So now you see that after we have a lot of tests, we have done a lot of tests. Some of them are really very fancy and you see looks very impressive. But mostly in the talk, you see, we only talk about mathematical formulas. I think that's the mathematicians always don't use too many images. Yeah, so now we come back to the mathematics. So essentially you see that so the method we used was essentially use a graph cut, and we have also segmented the same image with a continuous cut and those things. They are really very, very fast. But to get to those methods which has been used, you see, let's first start with the elementary models, and then you see introduce a level set method, skip those two, and then slowly come to here. You can see that what are the methods which has been used. So therefore you see that the elementary models for segmentation, essentially you see for image segmentation you can segment either on region-based methods or edge-based methods. So essentially you see there are really thousands of segmentation methods. You see that essentially they are just one of those two. It just depends on how do you use it. So therefore region-based methods is, you see that you give this image, you segment it into this one. So therefore there's region 1, region 2, region 3, region 4. You see this is the same region as that one. You have a more different component. So why you see that all the points here, they are in one region? That's because you see every point here, you see that they are more similar to each other than to the other regions. They are more similar to each other than the other regions. So therefore, which means I segment into this region because all the points in this region are more similar to each other than to other classes. So I segment into 1, 2, 3 classes. You see each point should belong to one class. You see that you see which class you belong to. You see that for this point is more natural. You see I put in this region is much better than put this, because you see the color here is more close to here than there. So this is because the region has a similarity, and this is a region-based. And so therefore edge-based, you see that I give this image, and then here are the segmentation. You cannot see the edges. That was essentially, you see these 2 points belong to the same region because there is a jump here, So this is based on the edges. And so those are the essentially, you see the segmentation essentially, if you're not the class 1, you must be class B, or you combine those two or use them in a separated way. So mathematically, I think those are most of the segmentation method. You cannot get rid of those 2 classes of ideas. So here is a Sneek model. So the Sneek model mathematically, essentially you see that you want to give a curve. A curve can be written x equal to s. You parameterize as 0 to 1. So therefore you see that if you want to simulate it, essentially you discretize this interval into, you see, many points. Each point will cause, you see here is a discretization of this parameter, and then each parameter will give 1 point on the curve. So therefore, if you want to move the snake, so essentially you move the corresponding points on the snake. So therefore you see that here is a curve. You see s may be equal to 0 here, and then you go around s equal to 1, you come back. You see that s0, s1, sn, so you correspond 1 point on this one. So therefore this is regarded as a snake. So therefore you see that you need to move those points. So how do you move the points? And let's see. You see that essentially you see that here is a snake. So you have an internal image, external image. So the internal image is you put the alpha s. So here x derivative square, beta x2 derivative square. And here is the integration of the edge detector on the curve. You remember we have also there's a plot here. And so therefore you see s is the arbitrary parameterization. If s is the real length of the curve, if f is the real length of the curve, this is a positive function, this is positive. If s is the real length of the curve, what's this term becomes? Sorry? It's a tangent. Yeah, that's a tangent. But here you see it's a vector. This is the L2 norm of the vector. If s is the length, what's the L2 norm of this vector? If f is the length, what's the length of this vector? It will be 1. If f is the length, x derivative is a unit tangent vector. So this become 1. And this is essentially the curvature, right? If s is the length. So this part is, if this is equal to A, this is equal to B, this is nothing else but the elasticus energy of the curve. So this is the length, this is the curvature. So this is exactly the elasticus of the curve. Normally you see S is not the length, so this part is proportional to the length, this is proportional to the curvature. So you are still, you see, minimize some kind of form of elasticus. You see that this is the external energy, so therefore this function is small if the curve you see drop into the valley. Yeah, here is external, so therefore you see this part is, you give arbitrary curve, integrate this you see this function on the curve. So that's this. So therefore you see if the curve fall into this value, you get the smallest value. So this is the energy. So therefore if you minimize such a thing with a curve, with arbitrary curve, your Lagrangian equation is essentially equal to this one. Is x derivative minus beta 2 derivative. And that's your Lagrangian. Mostly you add the time tx equal to the minus Euclid Lagrangian, and then you see when time goes on, the energy of the curve will reduce. So this is mostly the equation people solve with the Sneek model. And so you start with the initial curve. You start with the initial curve as this one, right? You use endpoint on this curve, and then you see that, and then here you xt mostly use x, you see that you use xin plus 1 minus xin divided by tau. So this is the previous position, and this is a new position. This is equal to this one, especially this part you can use the explicit formula. You see that you can approximate it by finite difference. You explicit formula, finite difference is finite difference. This is known. Then you can use this one to get the new points. You can use this one to get new points. And you iterate until you see that the point doesn't move anymore. That's where you want to get. And mostly you see that will. Yeah, mostly you see that if you start with the curve outside, if you iterate this one, this curve will just fall in down here. It doesn't move anymore. It doesn't move. So that's the simplest way to simulate the Sneek model. You solve this one, but there are more advanced methods to solve this one, right? So therefore, this is the so-called Sneek model, right? And this model, you see that you can only work with simple curves. So therefore, if you start with a curve here, if your initial curve is here, what may happen? Yeah, and then this term, you see, this term will make the curve shrunk. You see this term, you see that because integral of this one on the curve, you see it's similar. So essentially the curve will shrunk, in the end disappear. You get nothing, right? But if you start from outside, it will shrunk, and then the curve falls down to here, and then you cannot move anymore. So here, even you do iteration, so which means that this one doesn't differ from that one anymore, right? So therefore, you see, if you start with arbitrary curve here, you see, I think also you will shrunk to 0, to empty curve. So therefore, you see that it can only handle very simple situation. You see, for edge detection, mostly people use this one. This is so those could be also edge detection, because those functions also on the edge, it take very small value, but away from edges. So this is such a function is called edge detector. So this is a so-called edge detector. So this is a Sneek model. Yeah. This is positive. Yeah, it doesn't need to be positive. Yeah, because no, you don't need. But you can always shift up and down by constant. Right. You can also, you see, even if you want a positive, you just put a constant. That doesn't matter. Constant in the whole region. That doesn't matter, I think. So this is the so-called Sneek model. And so therefore you see that the Mumford-Shah model is essentially, you see that the Mumford-Shah model, I think for image processing nearly everyone knows. So the Mumford-Shah model is that you give an image U0 which may have discontinuities, and the Mumford-Shah model is to find the gamma contain many curves, could be open, close, and the function U which is smooth away from gamma. So U is each one away from gamma. This U should not have discontinuity, such that this is you control the length, or this lambda should be inside. So first this control the smoothness of U, control the length. In the region it should be mostly you take a p equal to 2. This is the so-called the Mumford-Shah model. Mumford-Shah model is really very, very well known. So therefore you minimize two things, U and gamma. This lambda should be here. So therefore those are two free parameters. So you minimize this one, so therefore you see that this U will be a smooth approximation away from the gamma, and this gamma should contain all the discontinuities. That's essentially, you see that's the essential idea. That's the essential idea. So therefore this is one real test for the Mumford-Shah model. So this is the input image. So you minimize the U, and this is the gamma. This is a U. So therefore you see gamma capture on the discontinuity. This U function, you see that on this gamma could have a discontinuity, but you see away from gamma should be very continuous. So this is a smooth approximation to this one, has discontinuity over all those points. So this is you give a U0, you give a right. This lambda still should be here. And so this is the Mumford-Shah model. So the gamma you see could be open curves. So you see here it could be open curve, it could be also closed curve. You see it could be open, closed. If you look very carefully here, you see that these principal discontinuity are captured. There's a lot of discontinuity here, and you see like a discontinuity here, so simply disappeared. And that's due to, you see, this lambda. If you choose lambda too big, and you ask your U function to be very smooth, and you can miss many of the small discontinuities. But if you slowly reduce lambda, you want to have more, you see that this could be more oscillatory, and then you will capture more and more of the small edges. You will be able to capture more and more small edges. But the Mumford-Shah is essentially you capture discontinuity plus you see when there is no discontinuity, you do a smooth approximation of a U0 in that region. And especially looking at this image, you can see that for image, the discontinuity are the most important information. If you capture the discontinuity, you know quite a lot about this image. So the discontinuity are the crucial things for image processing. So this is the general Mumford-Shah model. Yeah. In fact, the Mumford-Shah model, you see, we always call this Mumford-Shah model. In fact, exactly the same model in the discretized setting, so was already proposed in gamma. The Mumford-Shah model, this model is the discretized, is a continuous version. But the discretized version was already proposed, the same idea, same model was already proposed in the paper by gamma. So if you read carefully, you see that this model was already mentioned there. The Mumford-Shah just proposed in a continuous setting. All right. So this is the general Mumford-Shah. So you found the smooth approximation, and at the same time you found all the discontinuities. So therefore you see that how many discontinuities you found depends on lambda, also depends on mu. So those two controls how much details you may find. Right. Have you heard about Mumford-Shah from earlier? Right. Especially as you look at this image, I think it's very easy to capture. So therefore you see that if we require this lambda to be bigger and bigger, and then this U away from the discontinuity will become smoother and smoother. If you see let lambda go to infinity, that means we require, you see the very, very smooth U. And in the end, we just require U to be piecewise constant. So therefore, you just take, you see, very, very smooth. So there's no variation inside away from this continuity. I only allow you to take a constant. And then that becomes the piecewise constant Mumford-Shah. And piecewise constant Mumford-Shah, so therefore, and then you see that away from this continuity, I ask this one very regular. There's no variation. This must be constant away from this continuity. And then this term disappear, right? And then you see that you only minimize those two terms. You only minimize those two terms. So this is a so-called piecewise constant Mumford-Shah. So this U can only take finite number of constant values Ci, and those gamma is the discontinuity between the constant values. So you minimize the length of this continuity, also minimize the Ci, and U equal to Ci in omega I, such that this will be a piecewise constant Mumford-Shah. Right. And so this is, you require U to be very, very regular, very, very regular. And so therefore, and then you see that in this case, gamma must be closed curves. Why gamma must be closed curves? In the original Mumford-Shah, gamma can be any curve, right? Can be open, can be closed, can intersect with yourself. But if you require U to be piecewise constant, and then the curve must be closed curves. Why it must be closed curves? That's why, because you have one constant, so therefore you see that here is you see that you only take the finite number of constant, so therefore the boundary must be the closed curve you see around this constant region. So therefore you see piecewise constant Mumford-Shah cannot handle open curves, can only handle closed curves, But the general Mumford-Shah can handle, you see, more open curves. Yeah. And then the problem is how to solve it. I think, you see, if a gamma is given, minimize the Ci is easy. But the problem is how do you solve the curve? You see, how do you really, I know this curve, you see, this is the boundary curve, and this curve should minimize the energy. I think solve this one is more crucial, right? If we spare the most simple case, I just want two constants. And this is for image segmentation is like what I is in the slides. I just want to extract is one object and another object. Is one object the foreground, another object background. And in this case, you just need two constants. So therefore, I just need U equals C1 omega 1. This is the foreground. Everything I put into the background. So in this case, you see the Mumford-Shah become very, very easy. You minimize gamma is the interface between omega 1, omega 2, C1, C2. And this gamma is the length. So therefore you see that, and then the later term you can just split in the C1 manner, U0, omega 1, C2. So this is just a two constant case. And later you see we can see that the Convex was essentially, you see, starting with this one using level set. We are coming to the Convex very, very soon, right? So this is a two constant Mumford-Shah, And that's, you see, the mostly used segmentation model nowadays. More generally, if you have n constants, so therefore you see, assuming you see, and then you see in omega I take a Ci, so this term equal to this one. This is the length, you minimize omega and Ci, so you try to find the interface. So there should be, so here should partition the whole region, there should be no overlap and no vacuum. You see that especially handling this part is crucial. You see, when you partition the region, there should be no overlap, no vacuum. You see that this one intersect with this one, so which means there is no overlap. And this one equal to the sum, there is no vacuum. You see, for this kind of problem, you see, avoid overlap and do not produce a vacuum is two of the crucial things in the numerical technique. So this is the piece of a constant Mumford-Shah. So you use a finite number of regions, And so therefore you see that just in the last few years, and then the post model suddenly jump into image processing. The pulse model was originally, you see, proposed for material science. By Pulse was, I think he was a postdoc in Oxford in the maths department. And the Pulse proposed, you see, very simple minimization in the 40s or 50s, published in the Journal of Cambridge Mathematics. So the original Pulse model was very simple, have nothing to do with the here. Now here is later for material science, physicists. So they use this model. So essentially you see, you give a region omega. Give a region omega, and those functions fi from 1 to n, they are known. They are known functions. And the Pulse model is that you try to find the omega such that you integrate fi over omega I is minimized under, you see, with a regularization of the curves of the boundary lengths. And so here should be also no vacuum, no overlap. This is called the Pulse model. If you read the original Pulse paper, it has nothing to do with this one, but a lot of development later coming after Pulse, and this model is called Pulse model. This is called Pulse model. And so therefore you see that if you do this one, you can see that, so if a Ci are known, the piecewise constant Mumford-Sharp is reduced to the Pulse model if we just define this as Fi. If a Ci is known. So therefore, essentially, that's reduced to the Pulse model. So therefore, you see that here we have a Ci. Essentially, define this as Fi, and this is the length between the interfaces. So this is essentially the Pulse model. Do you see it?
But how can I calculate the Fi when I use the imaging?
Which value?
Fi.
Fi. Yeah, Fi. You see that if a yeah, this is Fi. You just define this one Fi. If a Ci are known. Yeah.
So,
assume you get Ci through another method or through some other approaches.
in general,
yeah, if a Ci is not known, and so I think you see that right. And then you minimize Ci. But if omega I is known, minimize the Ci normally is easy. So assuming you can do Ci is known, you define this Fi, you see the Mumford-Sharp, piecewise constant Mumford-Sharp model just is reduced to the Pulse model. Reduced to the Pulse model. And so therefore you see the Pulse model has been studied intensively for material science from physics. Right. So here is Minju, she was asking about what's a geodesic active contour. So this is the so-called the geodesic active contour. Yeah, so a lot of people say you see geodesic active contour is the same as Sneek Model, but maybe not exactly. The geodesic active contour is essentially, you see that I have an image, U0, your smooth image, so therefore even you see your smooth image, so this is edge detector, right? This is edge detector. And so where the U have a jump, this function will be small. This function will be small. So therefore you try to find the gamma. So here gamma could be open curve, could be closed curve, could be any curve. You try to find the gamma such that your integration of this edge detector on this gamma is minimized, but you regularized it with the length. And so this is essentially, you see, the one of the ideas of the geodesic active contour. But the geodesic active contour, in fact, if you read the original paper, what they want to emphasize is that they use a level set to solve it, and there is, you see, there's active contour moving. Otherwise, you can also use the Sneek model to solve this one. You see that this is essentially, you see that in the Sneek model, so therefore you see here you also minimize this part, and this part is the elasticos energy, right? And so this is the so-called geodesic. So therefore you see you can imagine that if this is edge detector, you find the curve such that this is smallest, and then mostly this curve will getting to where the edge detector is the smallest. You will get, you see, where this is smallest normally indicate there is a jump there. So mostly you will get most of the jump from this image. So here you regularize with the length. You see what kind of effect this length regularization may give you. If you don't use the length regularization, what may happen. Yeah.
Oscillation.
Yeah, if you don't regularize the length, so the curve will oscillate. The curve will oscillate. You see, oscillated curve, mostly the length is much longer. So if you regularize this one, and you still get a similar curve, but you kill the oscillation. Here you can even put on the elasticas, and then you see that you can even control the bending energy of that curve. The curve will be more smooth. So this will be this is a so-called geodesic acid contour. Geodesic acid contour, and then you see that here there's it is about, you see that the Convex, the piecewise constant, you see this region is segmented into one class, because you see they equal to the same constant, this constant, right. So essentially you have a function u, right? So you have a function u. And the piecewise constant moment for Xia is that essentially I approximate this u0 by a piecewise constant u. Right, by a piecewise constant u. So therefore this region is together because there's one constant. When they are equal to the same constant, you approximate original function the best. You approximate u by a piecewise constant u. So therefore this is a constant, and that's a region based. And then the geodesic, and then you regularize here is the length, the Euclidean length. So the geodesic active contour, you see, you put here edge detector, and then you regularize with the length. But you see that, so therefore maybe we didn't talk. So therefore you see that what kind of difference, the difference is the region-based and edge-based segmentation. See, just use your intuition, what kind of differences these two different methods can have. You see, in the beginning we talked about, you see that segmentation either should be region-based or either should be edge-based. So if it's you see, like the piecewise constant moment for Xia is region-based, and geodesic contour is edge-based. What kind of differences those two methods could have?
Use the image gradient for
Sorry?
Use the image gradient for
Yeah. Right, that's correct. Any other differences? Especially the young students, can you just do brief enough to guess what kind of differences? Huh?
one thing is a curve evolution.
Sorry?
Curve evolution.
Is
Curve evolution. Some make
yeah.
parameterized curve and then evolution, but
Yeah.
region-based model does not carry about such a thing.
Yeah, it's not only curve, you care about the region. Yeah. So therefore you see region-based method, you care about the region. Edge-based, so therefore the edge information must be very clear to make the edge-based to work. And so therefore edge-based, normally you cannot have a lot of noise. If you have a lot of noise, if you calculate the gradient, there's no clear edge. So therefore the edge-based may not work. But region-based, you see, essentially, you see, I look at here, you see that essentially this piece looks similar, another piece looks similar. That's very easy. So therefore the edge-based segmentation, you don't care about the region, I just care about the region. And that's normally more stable with noise. You can have a lot of noise, still if I look very far away, you see this piece looks similar, and this piece is darker, another piece you see brighter. So therefore the region-based is more stable. But however, the region-based method can also, you see that, also have a weak point. You may not capture the edge location very accurately. So therefore you see that, so this is a region-based. So here original, if G equal to 1, so this reduce the Euclidean length. But here if I also put the edge detector, and then you combine those two methods together, right? You combine, and then you have an advantage both of the region-based and edge-based. So you can easily combine those ones. Yeah. So therefore you see that nowadays you see originally the piecewise constant of Convex mostly just use length here. But I think one should really use put the edge detector. So therefore, so here you can think this is not a Euclidean lens, but it's a weighted lens. So the lens depends on, you see, you are on the edge or not on the edge. If you're away from the edge, it's a smaller, on the edge is, away from the lens is bigger, on the edge is smaller. So therefore, this will combine those two different methods. I think this idea has been proposed much earlier in the literature. When I talk about it, the Kimo said that he has a paper a long time ago. So I really cannot trace who was the really first one really proposed this one. I think just in some recent papers there's Bryson used this one. We also have used this one. But I think it can be traced much earlier. I'm not in a position to claim who is the first one to do this one. But this normally gives a much better result. Yeah. So here is the elasticas. We have talked about yesterday. You see that instead of using weighted lens, you can use elasticas as a regularizer. Yeah, here is like a zooming, the denoising. Yes, we talked about. You just take omega here. This will give you denoising, right? Here gamma. You see gamma is you want to do impinging, and then gamma with the region here. You put the gamma U0. You minimize this one, and then you will get the impinging. Zooming, you see, if you want to zoom 3 times, so you put, you see 2 new, zoom 4 times 3, and then you see those values are known. You want to find the curve away from those one, you minimize the elastica. So this is how do you do zooming. So therefore, the next thing I will talk about will be numerical techniques to solve, you see, all those models. You have those interface problems. You see, Sneek is one of the numerical techniques. But here, mostly, we will talk about, I think we will start with level set, and then we go to the graph card, and then you see there is several variant of the graph card. Maybe we take a 15 minutes break. Okay, yeah. We'll go to the numerical techniques. So one possibility is here we can go, you see, and then slow down a little bit, and we can have more discussion if that could be possible. If you know anything, have any question, just ask me. So numerically, you see that you see all those models. You need to minimize with a curve. You see all those models you need to minimize with a curve. You see here you minimize with a boundary. You see that how do you see really minimize with the boundary or minimize with a curve? And that's a numerical technique we are going to talk. So therefore, the first method we are going to talk is how to minimize with a curve or boundary is the level set methods. So the level set methods, you see that it's really, you see already is a classical. That's mostly due to Xue-Cheng Tai. I think many of you know level set very well. Maybe you have been testing with level set. So the level set method is essentially, you see that I want to move a curve. A gamma, most level set can deal with a closed curves. It cannot deal with an open curve. If an open curve, you must play with the special techniques. So level set, you need to deal with the closed curves. So if you want to deal with the closed curve, so therefore you see that Sneek model directly move the curve. You put many points on the curve. You put the endpoints on the curve, and you move the curve by such a formula. That's an explicit method. You move the curve, Sneek model. So the weak point of a Sneek model is, you see, one is the merging and splitting of the curve. That's getting very difficult. You cannot simulate very complete curve. There's other difficulties that you see that. Suddenly you see that for some application, you see those points may suddenly get very dense in one region and very sparse in another region. And then you get problem to trace a curve. You may need to increase the points somewhere. So those are the difficulties. So the level set methods is that you give a closed curve and then define a distant function such that this function is the distance to this curve. And then there's one-to-one correspondence between gamma and the function phi, right? So for any given curve gamma, there's a unique distance function. So there's one correspondence. So if you get this phi, you get this curve. So the level set method that when you want to minimize this curve, and you must move around to see which minimize the image, right? But the level set method is that you don't move the curve, you move the level set function. You move the function up and down, and that produces different curves. So therefore, originally is a minimization problem with the gamma, and then you transform it into a minimization with this level set function. And that's essentially the level set idea. So therefore, it's like this one, you see that you have a distant function. So you see you move the function down. So therefore here you cut it by the zero level curve. And this is a boundary, this is region, right? You move the function down, and here you see that these two regions are going to split. You move further down, you get two other regions. So I think this is the essential advantage of the level set methods. You see splitting and merging is very easy. So you see from here you see when this point is splitting, there's you don't need to do any surgery. But if you use a Sneek model, you see this point you must do a surgery here. Also when the level set come together. So this is essentially the level set method. So original minimization with a gamma with a curve, you become a minimization of with the level set function. And here mostly we require is a distant function. So it's a distant function. But some application like the segmentation methods, you don't require a distant function. Any positive function, positive inside outside is enough because I only need the curve. So inside you may get multiple values, just if you produce this curve is enough. But so for some other application, you need to enforce this distance condition. And this is I think Stan Osher's most favorable work, and this is very influential, right? So therefore you see that how do you move a level set? As you have a one level set, mostly you have one curve. But mostly you see, let's say we want to move the curve, so which means our curve depends on time t, right? And also you see that this is S is a parameterization in the Sneek sense, t is a time, so therefore S goes along the curve. When t moves, the curve move up and down, right? So therefore you see that assuming this is gamma t, this is the corresponding level set function. You also add the t here. Originally we only have x, right? So therefore you see that if you want to move this curve, what kind of movement you should have on the level set function t, right? So therefore originally you see the Sneek model move the curve, but use the level set method, we don't move the curve, we move the level set function. You see that what kind of if one movement of the curve, what kind of corresponding movement you must have on the level set function. So this is essentially, I think this is well known. You see every people who have been working with the level set, you know about this one. So therefore you see that, so this is a curve, phi on this curve equal to 0, right? And so therefore you see that this curve originally this parameterization with the level set, and this curve expressed in this way. So therefore if you differentiate this one on the curve, this function with t, so assume in 2D, so here you get gradient, right? Inner product with xt, so that's coming from, and then you get phi t, right? So if you differentiate with t, and that's what you get. Assuming you see that in the Sneek model, you want to move the curve with a velocity equal to this one, if this is the velocity of the curve, right? So therefore if this is a curve, and so every point I move it with the velocity t, and so this will be the movement in the original Sneek model, right? So therefore if you put this one into here, so you get vt equal to this one. We know that so this vector is what kind of vector for the zero level curve? This is a unit normal vector. And so therefore if you inner product with this velocity with this one, this will be the normal velocity of the curve. So therefore you have arbitrary v, so this will be vn, so this will be v tangent, this will be v tangent. So therefore you see the tangent velocity, the tangent movement doesn't change the curve, right? You just make the curve running around. Only the normal velocity changing the curve. So therefore you see that when you give a velocity, so you shouldn't do anything, you should just use a normal velocity to move the curve. So therefore if you define this one as a normal velocity, so therefore if you put it there, here should be plus, here should be plus. So therefore you see that if you want to move a curve with a normal velocity Vn, so here should be plus. So therefore it's equivalent, you need to move the level set by this equation. So this is a well-known level set equation. Right. If you want to move a curve with a normal velocity Vn, you just solve this one and then the corresponding zero level set will be moved according to this velocity. So this is a well-known level set. This is a stanza, you see, first invention, right? But there should be Vn there. So this is the level set methods, right? Also, you see that if the level set is given, so therefore this will be the unit normal vector to the level curve, including zero level curve, and this will be the curvature. If the curvature for the zero level, so therefore you can easily, if a phi is given, you can easily compute the curvature. If phi is a distant function, and this reduces to the Laplacian of phi, why? If phi is a distant function, the curvature is just the Laplacian function on the curve. Why? Yeah, if the distant function, and this will be always equal to 1. So therefore you see that, and then you just reduce it to the minus Laplacian, so you can easily calculate. So therefore also from the level set function, here is a Heavyset function. Heavyset function where phi is bigger than 0, Heavyset equal to 1, less than 0 equal to 0. So this will be give the area of the positive region. Yeah, so here you see that the Heavyset phi is a characteristic function of the region, right? So therefore this is what we talked yesterday. If you calculate the total variation of the characteristic, this give you the length. This is gamma is a boundary of D. So therefore another way you see here, you can write it like a delta phi. This is very informal. This is very informal. Very informal. So therefore you see that if you know the level set function, you can get all those geometrical quantities. So the area, the length, the curvature, the normals, and you have everything. You can express everything of those things by the level set function. So therefore you see originally, you see many problems, we need to minimize those things. If you transfer everything to the phi function, and the original minimization on phi, it becomes a minimization with the level set function. So this is essentially the level set idea. You see, for some applications, you need to really enforce a distant function. You enforce a distant. So therefore, enforce a distant function is essentially based on here. So given closed curve gamma, the distant function is a viscosity solution of this equation. So this is essentially you see that phi x squared plus phi y squared equal to 1. And this phi should be, you see that mostly this gamma is given. Phi equal to 0. In the rest of the region, you should satisfy this equation. The distant function is a viscosity solution for this equation. You see, 1D is very easy to understand, right? So 1D, I think 2D is not difficult, but 1D, you see, it's a very easy to understand. So therefore, you see, in 1D, gamma mostly reduces to some points. In 2D, gamma is a curve. 3D, gamma is a surface, right? And so therefore, the distant function, you see that the distant function here, it depends on which one is near. If it's here, the distance is a middle. So therefore, the distant function, the sunny distant function is just look like this one, right? If this is a gamma, you see that if this is the interior, and this is the interior of the region, this will be exterior of the region. And the sunny distant function, this is the sunny distant function. So therefore, this function has a singularity in the middle of the region, right? But otherwise, you see this slope, the slope of this one is just exactly equal to 1 because x equal to y, right? So therefore, the slope is 1. So therefore, here the phi derivative equal to 1. So here the phi derivative equal to minus 1. So phi derivative equal to positive 1, phi derivative equal to minus 1. But the absolute value is always equal to 1, right? So therefore you see that, so to compute the distance function, essentially you try to compute the viscosity solution for this one. And that should be enough. In 2D, you see that, in 2D, you see if this is your curve, right? If this is your curve, and then you see that, so here is, you see the distance. So here is the level curve of the distance functions. So in the end, you see that you become this skeleton. So therefore, in 1D, the function is singular at the middle of the region. In 2D, the function will be singular at the skeleton. Right? But you see that essentially you see that if you make a tangent, for every point you draw the tangent, so the level curve should be orthogonal to the tangent, and then you see if these two lines meet here, you see if those two lines meet here, this point must have a singularity. But on this curve, you see that was essentially the distance to the curve. Right? So this is, if you really need to calculate the distance function, you try to calculate the viscosity solution. So therefore, you see, mostly we use, you see, the very old methods with the standby damping Yang. We use it. So essentially, you see that they do a time marching and do a characteristic updating here. We use this one to update to calculate the distance function. And so therefore, a lot of people use time marching, fast marching. So fast marching is essentially, you see, 2D, you start from this point, you check, you see which points are near, and you expand the distance function larger and larger until you compute the distance function in the whole region. And so those are the methods we have been using. Even this one is very easy to use. It was just characteristic upwinding. You do explicit, and here you do explicit. So mostly we use that method to compute. And that's, for most cases, is sufficient. But fast marching could be more accurate. Yeah. So in case you may need to read distance, you need to calculate distance function to a curve. Right? So therefore you see that and the Convex method, which is one of the most popular segmentation model. I think Convex has become so popular. If you Google search, so it's unbelievable. You see that how many places they have been using Convex. You see, even there are people implement the Convex over the Samsung handset. They have a code which you can run the segmentation on your Samsung mobile telephone. That was really unbelievable. So essentially the Convex method is essentially to solve this two-phase piecewise constant Mumford-Sharp by level set method. So therefore piecewise constant Mumford-Sharp by two constants. So essentially you have omega 1 C1, omega 2 C2. This is the length, you minimize the length. So therefore you see that how do you solve it? You don't use Sneek Model, you use the level set method. So therefore you see that one level set should be positive in omega 1, negative in omega 2, and 0 on the interface gamma. So you introduce one level set function. So therefore, once you introduce a level set function, you see that originally minimize the gamma. How do you become a new minimization with phi? C1, C2, you don't do anything. You don't do anything, right? So how do you transfer the minimization with gamma to a minimization with phi? So this is how do you transfer. You see, the length, the Heavyset function is a characteristic function of region omega 1, right? So therefore, the total variation of this characteristic function becomes the length. So therefore, alpha delta Heavyset phi, this produces the length of the interface. This produces the length of the interface, right? And then you see that in omega 1 should be closest to one constant. So therefore you see that this C1 is essentially C1 minus U0 squared. This 0 should be under script. So therefore if you just put the Heavyset, you see this is 0 in omega 2, So this term exactly equal to that term, right? Because Heavyset equal to 0 omega 2. If you just put the Heavyset here, you just can integrate on the whole omega, right? And similarly, the 1 minus Heavyset, so therefore you put the 1 minus Heavyset and this omega 2 disappear. So here is the omega, and then you see gamma, omega 2 completely disappeared. And then you see the minimization with you see gamma. You can now just minimize with the phi. If you get a minimizer of phi, you get a minimizer of the original problem. You get a minimizer of the original problem. So this you transfer a minimization with the interface. You transfer it to a minimization with the level set function. So you just move this level set function. That's enough. That's enough. Right. So this is the essential point. You don't move the curve, you move the, and now you can just move the function phi. And this is the Convex methods, right? So it's really looks a very, very good idea. It looks simple and very, very elegant, right? So therefore you see that Heavyset is just defined here. Heavyset, so the Heavyset function is essentially, you see that equal, so here is x, here is Heavyset. Heavyset equal to 1 here, 0 here, right? This is the definition. So from phi you see that the where bigger than 0 you get phi negative, and the interface give you the interface. So therefore this is become the Convex methods, which is very easy to solve now, right? Looks very, very easy. So in real simulations, so therefore I think the original paper you smooth this Heavyset function. So the Heavyset really jump directly from 0 to 1 here. In real application you do a small smoothing. You replace Heavyset by Heavyset epsilon. So therefore you see delta function by corresponding delta epsilon function, and you minimize this one. So that's what you do. That's what you do. Yeah. So here you see that if we define, so here is the C1, C2, here is the phi. We define the minimum wisdom with phi with C1, C2. So here is you want to calculate the use principle of variation, and you perturb, you see phi by epsilon mu arbitrary function. You try to calculate this one. Oh, there is a mistake. Here is a mistake. So therefore, you see this is essentially that you try to verify. You see that if phi should minimize the energy, and then this variation must be 0 for arbitrary mu, right? If phi should minimize this function, this is arbitrary function mu. If phi should minimize this one, and then for arbitrary mu, this limit must equal to 0, right? Because when epsilon goes to 0, that's the smallest, so that should equal to 0. So therefore you calculate the variation with phi. So therefore you replace here phi plus epsilon, epsilon mu, phi epsilon mu, and you calculate. So therefore you see that those two terms are very easy, because this one disappear. So this one minus that one, and then you get the delta phi here. You get delta phi here, right? But then here is a mu. I have missed the mu. You have a mu here. So this you just do the simple calculation, calculus of variations. And the length term, you see that length term of variation, there is also, I miss a mu here, come to here. How do you calculate this one? Take a little time. If you want to go through it, so we can go through it together, right? So the minimization of this one become this one time of mu. I miss a mu here, and that take a little time to calculate. Yeah. Mu is arbitrary. You perturb phi by arbitrary. Epsilon is constant. Mu is arbitrary. Oh yeah, I'm sorry. Yeah, I'm sorry. Maybe I shouldn't use a mu. So here should be a phi tilde or something, right?
And then I think for the computer term, so you also need the delta function, right?
Sorry? Oh yeah, here you overfit. You will overfit. Yeah.
No.
Here should be phi. Here should be phi.
And then,
Phi here, phi here.
And then times and then delta phi, right?
What? Yeah, here should be fine.
And the delta phi, and then even in the last one,
Yeah, here should be fine.
yes,
Fine.
from the fidelity term, we get the delta phi, and then the first term, and then in the second, in the last equation.
Yeah, this
last
one?
part,
Where?
no, in the curvature.
Here.
Yes.
Yeah, this should be fine.
No. Times with this whole this term,
Yeah.
times and delta phi, right?
Yeah, that's right. That's right. No. So let's write down the correct one on the blackboard. Yeah, so therefore you see that f phi equal to all those things, right? So therefore essentially you see that we put f phi plus epsilon, maybe here, yeah, because mu is a constant, I should use another function here. Because this I did it on Sunday very quickly. So therefore you see that there's not enough time to check.
Epsilon times eta.
Eta, yeah, eta, right. So for example, you see that, and then this is a phi ci. You see that when epsilon goes to 0, if a phi is a minimizer, and this should be 0. This should be 0 for arbitrary eta. So therefore you see that this one, for the fidelity term, it's very easy. You get the delta, this one disappear. So it's here, this one is correct, right? This one is correct. So therefore, and then you will get what exactly is written there, which is C1 minus U0 square, C2 minus U0 square, delta phi. For this part, so therefore for this part, yeah, should be equal to mu delta here delta phi times eta. Yeah. How do you come from here to here? There's a little trick. It's not very obvious. It's not very obvious. There's a little trick to come to here. Yeah. But at least a variation of this one equal to this one. It's also integral, right? Right.
You need eta in the first.
Yeah, also add down here. Very good, very good. So if you do a variation of that one, so that means you see that if phi should be minimizer and this one should be equal to 0. So which means that C1 minus U0 square minus C2 minus U0 square delta function phi. Oh, here there's also, I missed a delta phi here. Here there's also delta phi. And so here is the minus mu divergence phi delta phi. This is equal to 0. If a phi should be minimized, this should be 0. Mostly you see in numerical we do a smoothing here. You see mostly in the original methods, so therefore you just do equal to minus plus. This is you move a phi function in the negative gradient. So you put the minus here plus. So that will be the negative gradient flow for phi function. I think I have it somewhere here. You see that if a differential with C1 is very easy, right? If you want to minimize with the C1, you just C1 is a constant. You just differentiate, you get 2 C1 minus U0, and this should be 0 if a C1 is a minimizer, right? If a C1 should be minimized, this should equal to 0. And similarly, C2, you see, you just get the minus, but it doesn't matter, right? It just doesn't. Yeah, I miss also minus here. You see, that's due to Sunday. It's not because me. So here I will be minus because there is a minus here, right? So C2. So therefore, if a C1, C2, and phi should be minimizer for phi, so this must equal to 0. For C1, C2, those two must equal to 0. And so therefore, you see, how do you use the two-phase term? They say that you do. There is a delta phi missing here. Also delta phi missing here. So you do a gradient descent on phi. Use this equation. C1 equal to 0, and you see this one equal to 0. So this one equal to 0. So therefore, you take a 2 away. C1. And so therefore exactly you get this formula. So C1 is equal to this one. So this is essentially integrate U0 omega 1. This is the area of omega 1. So that's just the mean value of U0 in omega 1. And this is the mean value of U0 on omega 2. So this is the Convex method. So therefore the simple way is still there should be phi here, delta phi here. So therefore you can just do an explicit time marching. You see that do many iteration of this equation of the C1, C2, do many iteration of the C1, C2. So this, I think this was the original algorithm which was used in the Convex paper. Yeah. So you can see that essentially you see that you don't minimize with the curve anymore, you just turn it into a minimization with a level set function C1, C2. So if you need more than one region and then you use a two level set function, you can produce four regions, right? You see one level set function where it's bigger than 0, bigger, less, bigger, and then you produce a four region if you use two level set functions. So therefore you see that if you know that you exactly want to find four regions and use a two level set function, your original four region thing can really be, I think here is a multi-phase Convex set. So therefore you see that I give a U0, I want to segment it into four regions. So essentially I know I only want four regions, and then what you do, you see that here is your U0, here your U0, and then you use two level set. You use a phi 1, phi 2, C1, C2, C3, C4, and so here will be the length of for the boundary for the phi 1 level set. So here will be length for the boundary for the phi 2 level set. So that was essentially, you see that. So the first one calculate this length, and the second one calculate this length. So you minimize the sum of those two lengths, and then you see that. So here is essentially, you see like so here is a region omega 1. You see C1, omega C2. So this is each region. You see that each region U0 minus the corresponding constant. So this is essentially if you want to use the Convex set. So now you need to know exactly you want to have four regions. If you need more than four regions, and then you need one more level set, and then that can produce up to 8 regions. If you use so that 3 level set produce 8 regions. 4 level set produce 16 regions. So in this way you can increase the number of level set, you get more and more regions. But I think you see for level set, if you need more than 3 level set, and then the calculation is becoming rather complicated, because you see that you see one level set. This is the equation. You need 3 level set. You need you see you have a multiplication of a delta Heavyset, and those 3 nonlinear equations need to interact with each other, especially if you use an explicit you see method to solve it, and you see that may not be easy. I think we have tried 2 level set. You see 2 levels are mostly still okay. If you use 3 or more level set numerically, so that's really could be something a challenge. So therefore you see that the Convex method, why it's getting so popular, so many people use it, essentially use level set for sexual Gaussian, can handle very complex geometries. So therefore you see that this is one of the advantage. It's like a Sneek model, you cannot handle very complex geometry. It's a region based, robust with noise, and you can segment the images. There's no edge, right? So even like this image, if you want to detect the edge, you will get something completely different. But if you use a region based, so therefore you don't use the edge information. If you really calculate the edge information of this image, detect the edges, you will get something quite different than what you get here. So therefore you see that And I think those are the two important reasons why the transversal are getting so popular. So therefore, then you see that still have some disadvantage. We need to get better. So what are disadvantages? Slow in convergence. Even you see you get other way to solve it, it's still slow. And then the other thing is that it's non-convex. It's non-convex. So the minimization problem is non-convex. It's convex with a C1, C2, but non-convex with a phi. So therefore you see that even in the two-phase case, you see that the minimization with the phi is non-convex. So due to Heavyset is non-convex. So with the phi is non-convex. So due to non-convexity, if you minimize the non-convex function, so therefore you see that you could easily get stuck with local minimizers, and so therefore it depends on the initial value. So this is I think this is common. So this is you segment the cameraman. So here is if this is your initial curve, you segment this man out, and this is the boundary. But if you start with this curve, and this is what you segment the upper part of the ocean too. So it depends on the initial value. Even I think there are many examples. I think I have a movie. Yeah. So this is very common. This is very common, right? So the slow convergence and dependence on the initial value. So those you see we can overcome those things by some newer techniques. So therefore you see that piecewise constant level set method, so this is essentially you see that so we don't you see the somehow related to the graph cut. Maybe I'm thinking we can skip this part. Also the phase field, I think phase field for people working with material science is very, so we can also skip the phase field. Maybe I don't know, you see that we don't have much time. We should stop here. Yeah. So the convex relaxation, you see that you currently global minimize, you get very easy computation. And so there you see we have a proof, and then I'm going to explain the essential idea of the convex relaxation. And especially you see graph cut, you see I'm going to explain exactly, you see the graph cut, we'll solve this one by graph cut. It's exactly minimum. You see, if you don't regularize, reduce it to the K-mean. Reduce it to the K-mean. And if you regularize, this exactly becomes the transversal model. So there is a clear connection between the graph cut and the transversal model. And so therefore you see later we found out, you see that you see the graph cut, you don't need to solve it by graph cut. You can formulate it as a convex minimization problem, and then there is no graph and nothing else. Those connections and you see those part is very new, mostly overcomes the difficulty we are talking about. So this part is quite exciting. It's quite exciting. So therefore, hopefully you see that we can go through this part together in a very careful way, such that you understand it. Also, in the end, I'm going to give you the code. So the code is public. You can download it. You can test it, really very very fast. So it seems that we need to stop here today. Okay, thank you.